Hey AP, this video is going to be on compounds, isotopes, and mass spectrometry or spectroscopy. Compounds and isotopes are things that we've learned about before back in chemistry, but mass spectroscopy is new. So we'll spend most of our time on that. So again, these notes follow along with our text that we use. And so you can either use the videos to fill them out, or you can also use the chapter to fill them out. Obviously, I'm going to explain things as we go along. So at the beginning, some definitions of things that we have learned before. So an element, a substance that can't be broken down into other substances by chemical means, made up of one type of atom, whereas a compound is a substance formed with multiple elements bound together in a fixed composition of atoms, right? Atoms come together, they make a compound. If I have something that's pure, it can either be pure because it's one singular element, or it could be one type of compound. So if I have a container of carbon dioxide, and it's just carbon dioxide inside of it, that's a pure substance. However, something like air, which is a mixture, is made up of lots of pure substances, so that's different. And that goes into our next one, where a mixture is made up of multiple pure substances and can be of varying composition, either homogeneous, which means uniform. I can't see the difference, like air is homogeneous mixture. I can't see the different particles in it. Or heterogeneous, which I can see different distinct regions, such as sand is a heterogeneous mixture. Compound formulas, they show the exact ratio of atoms of elements present in the compound. Remember that subscripts tell us how many of each atom are present. So I have something like H2O. That means I have 2 hydrogen atoms, nothing after the oxygen. So there's 1 oxygen atom. Empirical formulas are the lowest whole number ratio of the atoms of each element in a compound. And very different compounds can have the same empirical formula. So I could have the empirical formula CH2, which can also be an empirical formula of something like C2H4, C4H8, C8H16, right? This is my empirical formula. It's the lowest whole number ratio of carbons to hydrogens. These would all be molecular formulas because there's some multiplier bigger. This is how we calculate empirical formulas. Again, a review of what we have learned before, where if we have percents, we turn them into grams, divide by molar mass to get to moles, divide by the smallest one to get a ratio, and we multiply till whole if we can. Remember, if we have experimental data, we don't really multiply until whole because usually there's some rounding error in there, especially because, we're taking real life measurements. And then again, the molecular formulas tells exactly how many of each atom are present as opposed to the simplest whole number ratio, some multiplier bigger. So M for molecular, M for multiplier bigger. So for example, a hydrocarbon, which is the compound containing only hydrogen and carbon, found to be 7.69% hydrogen, 92.31% carbon. An impure sample of the same hydrocarbon is found to have a percent by mass of carbon that is 80%. Is this observation consistent with an impurity that contains no carbon? So what is this asking us? It's asking about a pure substance versus an impure substance. So my original substance that is pure, and I like to draw pictures because I'm a very visual learner. So if I have this pure substance here, it is approximately 7.7, we'll say, percent hydrogen, and the rest, 92.3%, is carbon. Okay, and then an impure sample is found to have a percent by mass of carbon that's 80%. So impure, I find that has 80% carbon. Does the impurity contain no carbon? Well, if my percent of carbon went down, even though I added an impurity to it, that means that I almost diluted my amount of carbon that was in my sample by adding in other things and decreased the percent. So, is this consistent with impurity that contains no carbon? Yes, because the percent went down. Okay. If it had carbon in it, my percent would have gone up. Okay. All right, so that is for most part review. Moving on to our next part, we've got the mole. Again, the mole is also review. The mole is a standard number of particles based on the number of particles found in 12 atoms, of carbon 12, which were the number of atoms in 12 grams of a carbon 12 isotope. Avogadro's number is how we quantify the mole, 6.02 times 10 to the 23rd, which I believe, is that on your reference guide? I don't see it. All right, so that's a number you're definitely going to need to know. Yep, and most of you do know that one. Atomic mass units, AMU, is the reason that we can use the mole and can determine molar mass. Other names for molar mass can include relative molecular mass, or RMM, or relative formula mass, which is RFM. Majority of the time, I think except for like one circumstance, we'll use the term molar mass. Mainly that just keeps us consistent because that's what we learned and talked about last year, and that's a pretty common language in AP as well. Then we have isotopes. Isotopes are atoms with the same number of protons and electrons, but different number of neutrons. Okay, isotopes have a different number of neutrons. Therefore, they also have a different mass number, right? Because my mass number is my number of protons plus neutrons. The discovery of isotopes disproved one part of Dalton's theory, and he said that all atoms are the same, so all carbon atoms are the same. But now we know that that's not true. We can have carbon 12, carbon 13, maybe carbon 11, carbon 14, and those are all varying number of neutrons. We can show isotopic notation, where we have the mass number over the atomic number and then the symbol. You could have a charge here, but remember, isotopes don't have a charge. So for example, if I had carbon 14, that'd be 14. Carbon is number 6, and then I'd have the C for carbon. Okay. So looking at isotopes, we realize that if I have a pile of carbon, I could have some carbon 14, some carbon 13, some carbon 12, some carbon 11. And so if I'm looking at their masses of all of them, really in my hand, I need to have an average of those masses. And we also take into account how abundant or prevalent each one of those isotopes are. If there's more carbon 14 than carbon 11, it's going to be a heavier substance overall. And so the way that we do that is we calculate relative atomic mass, or molar mass. You have also seen this as the average atomic mass. And it's a weighted average of all the masses of the atom of the isotope in a sample. And we get that by our formula. And we say that it is the percent of each isotope times the atomic mass of the isotope. And then divided by 100. And this is the sum of each of those. So remember, this means sum of. So that means it is the percent times the mass plus the percent times the mass, and so on and so forth. And we divide all of that by 100 because we have percents. And that gives us our average atomic mass, or the relative atomic mass. Okay. So again, thinking about isotopes, what we can also do is we can graph this information. And the way we can graph it is we can use something called a mass spectroscope, which can detect the isotopes and their abundance in a sample. And then it spits out a graph and it tells us how much of each isotope is there, which is how we could figure out what is in our sample that we have. So first new concept is mass spectroscopy. It is used to detect isotopes and provide evidence of their existence. It ionizes beams of electrons by turning atoms into positive ions. Then positive ions are going to be attracted to negative. So ions are sorted by mass, and then they see which isotopes are present. So we'll do a POGL tomorrow. I think you started it today. And in that POGL, we'll look at how a mass spectrometer works. So we'll get to see how this happens. But what we end up getting is this printout, and we can have both the printout of the isotopes and their percents, but then we can also graph this information. And in a mass spectroscopy graph, we have our title of our element. So in this case, we have chromium. We have the mass to charge ratio, okay, which is our charge. We charge them by turning them into a positive ion, which is 1. So really, these are just mass numbers at the bottom. And then the relative intensity goes on the side, and that is very similar to abundance. So we can say it's kind of like abundance. Which is what we've used before up here. So from this data, we can see that we have 4 different isotopes and differing levels of relative intensity. So I have here from 0 to 100, and then I just took a chunk out of my x-axis from 40 to 64, putting 52 in the middle, going down to 48 and 54. So this is 50, and then this isn't a very good graph. Let's see, 50, 51 is there, 52, 53, 54, and so on. So at isotope 50, I am up 4.3%. So isotope 50 is here. 4.3% is pretty small, right about there. Probably less in reality. 52 is at 83.7%, so much higher. About, let's say here. Have to draw a straight line. 52. 53 is 9.5, so about twice as big as this one. So about here. And then my last one, 54, 2.3. So about there, probably smaller. We can make this one maybe a little bigger. Make it proportional. Okay. From this, I can easily see that my most abundant isotope is isotope 52. Has the highest relative intensity. It's the most prevalent. It bombarded with the sides the most. And that my lowest intensity one is 54. If I look on the periodic table at chromium, which is here, I can see that chromium has an average atomic mass of 52. Well, that makes sense. It matches up with the most abundant isotope that I have is isotope 52. And there should be that correlation, because what I could also do is I could figure out my average atomic mass for chromium by taking my percents times my isotope, adding them up, dividing by 100, right, using this formula to get my average atomic mass for chromium. Or I could use this data and, ballpark my numbers across the side. Okay, so this is a new graph that we'll see and we will interpret and use. So how would we do a calculation that has to use a mass spectroscopy data? Let's take a look at one. So our first example here asks us to sketch the mass spectrum that you might expect to observe if bromine were passed through a mass spectrometer. Oh boy, here it goes. 2 common isotopes of bromine are bromine 79 and 81. They're known to exist in approximate 1-to-1 ratio like chlorine. Bromine is also known to form diatomic molecules. So we can have, move this. Don't want my hand in your way. So I can have bromine 79, and we can have bromine 81. And that's what it tells us here, 79 and 81. It doesn't tell me my percent abundance of either one of these. It just tells me that I have 2 isotopes and they're going to, come together to make 100%. It also tells us that bromine makes a diatomic, which we know. So I can have bromine as a diatomic. And if it's a 1-to-1 ratio, that means I could have bromine 79 and 79. I could have bromine 79 and 81, or I could have bromine 81 and 81. Okay, those can be my three combinations if I have two isotopes and it makes a diatomic. Okay, so we eventually want to sketch a spectrum. So I need to know the percent abundance of each of my two isotopes of bromine and my diatomic bromine. So my mass numbers of each of my diatomic bromines are 79 is 158, 160, and 162. So that means in my graph, let me get down over here. I have mass to charge, which we show as capital M/E at the bottom. And then we have relative intensity on the side. And we know that that goes up to 100. My mass to charge, my options are 79, 81, and then these. So I'm going to include all of those on my graph as well. So, and I'm just going to record 79, 81, a jump, 158. These do not have to be to scale. 160 and 162. So I know that those are my isotopes that I'm looking at. Okay, and I need to figure out relative intensity. And that's where we're going to use our average atomic mass calculation here. But we don't know percents, but we do know algebra. So if I have a chunk of just atomic bromine, so just Br, okay, I know that some amount is bromine 79 and the other amount is bromine 81. If I don't know the exact percents of each, I do know that this is out of 100% and that this chunk here, if we call X, okay, if we say this is some amount X, that means that this white area here that I'm shading in is 100 minus X, because it's the rest of the pie, total of 100%, minus the chunk that I colored in. Okay, so I can do that same thing for my isotopes. Okay, so I can say that bromine 79 is X, and bromine 81 is the rest of it, 100 minus X. Okay, I can pull from the periodic table the average atomic mass of bromine, which I can see is 79.9. So I know that 79.9 is equal to my average atomic mass calculation. So my percent X times its mass, 79, plus my other percent, 100 minus X times 81, all divided by 100. Okay, so simplifying from there, 79, then I've got 79X plus, now this has to be distributed, right? Foiled through. So I've got 8,100 minus 81X. Continue to combine like terms and then move that over, and I end up with 2X equals 110. Okay, that's by 79 minus 81 is 2. Brought that over so it's positive 2. Subtract 79.9 from both sides. And, oh, sorry. This will divide by 100. So I multiplied this side by 100 and this side by 100. My apologies. Skipped a step. So I turned that into 7,990 because I had to get rid of this guy. So then So my 2x came over here, subtracted 79.90 from both sides, and I got 110, which means that x equals 55. So that means that my bromine 79 is 55% abundant, and my bromine 81 is 100 minus 55, which is 45% abundant. So that means I can now put that on my graph. So 79 goes to 55, which is a little higher than 50 here. And then 81 is about 45%, so just a little bit less. So now I have those filled out. And next, I'm going to go after my bigger one. Well, now that I know my percent abundances of my each of my individual isotopes, I can estimate a little bit as to what my isotope differentiation would be for relative intensity for my diatomics. So I know that my 79 isotope is the most abundant. It's at 55%. So if I have the combination of my two most abundant things, this one is going to be the most abundant diatomic. Which also means my 81 and 81, the two least abundant isotopes, those are going to have the least common outcome. So they're going to be the least abundant, which means this guy is going to be in the middle. So if I know that it's about a third each, we can say this is more than 33%. This is less than 33%. We can maybe say this one's about 33%. So 158 is going to be the most. Put it higher. 162 is the least, lowest, and then my 160 is going to be somewhere in between. And we can make that educated assumption based off of our data here. We can make that from there. All right, one last thing. You're holding on. Okay. I apologize. These videos are a little longer than your ones for last year. There's just lots of good information. I want to give you lots of examples while you're at home so we can really jump in when we get to school. So this one's a little bit more straightforward. I have the mass spectrum for titanium, produces peaks according to the following data. And here I just got the printout of my relative abundance versus my mass to charge ratio, which we know is very similar to my mass number for each of my isotopes. Use the data to calculate relative atomic mass of titanium. Well, we know that relative atomic mass is equal to my percent times my mass, add them up, divide by 100. This is just a calculation. So, showing our work, my relative abundance, 8.25, times its mass, 46, plus relative abundance, 7.44, times 47, plus 73.72 by 48, plus, this is a long one, 5.41 times 49, plus 5.18, ran out of room, times 50. All of that divided by 100, and I did this ahead of time. So when I plug this in my calculator, I get 47.9, and my units, because this is an average atomic mass or a molar mass, are grams per mole. And I could double check that by looking at the periodic table. When I cross my fingers, that it matches. Titanium, 47.9. 47.9. I have done it correctly. All right. That concludes our video notes on compounds, isotopes, and mass spectroscopy. And we will come to school tomorrow and continue to practice and practice and practice some more.